I'm Cameron.
I'm Addie.
I'm Presley.
I'm Carter.
I'm Alicia.
I'm Huck.
Why didn't you stop filming?
Okay, so I'm going to be talking about the action potential graph and how and the voltage gated ion channels for sodium and potassium. So I'm going to start by explaining resting potential and threshold potential. So you can see here at resting potential there's not enough energy for anything to happen. So the synapse doesn't have enough energy to like have any kind of reaction or activity.
My ice cube.
But then once it hits the threshold potential, then it can begin depolarization, but Presley's going to talk about that later. So for right now, I'm just going to talk about the gates. So what happens is that there's a changing electrochemical potential throughout the action potential graph. And this is because of a difference in charge between the outside and the inside. And then the protein channel is designed for sodium and potassium ions to come in. They have like these gates, and the gates, so in the charge, in the initial gate, then like when it gets too high, then the next gate opens and the charge moves on. And so that's like the potential of it. Yeah, another channel opens to let it out. And yeah.
It's Addie, and I'm gonna talk about facilitated diffusion and active transport. So facilitated diffusion is the passive movement of molecules across a membrane through specific channels or carrier proteins. It does not require ATP because the particles move down their concentration gradient from an area of high concentration to low concentration. So in neurons, sodium and potassium ions move by facilitated diffusion through the voltage-gated ion channels during the action potential. And then the rate of facilitated diffusion depends on the number of transport proteins available. And then, so for active transport is the movement of substances across a membrane against their concentration gradient. So it would go from low concentration to a high concentration, and this requires energy in the form of ATP, which is unlike facilitated diffusion that doesn't need ATP. This process uses carrier proteins known as pumps, and then in neurons, specifically the sodium-potassium pump actively transports sodium ions out of the cell into potassium ions into the cell. This maintains the resting membrane potential and restores the ion gradients after an action potential.
In the action potential graph, there are two phases. There's depolarization and repolarization. During depolarization, the change in charge from negative to positive, and in repolarization, it's a change back from positive to negative. These charges change by moving sodium ions and potassium ions out of the axon. Depolarization is when sodium ions flow into the axon. Repolarization is when potassium ions move out. Sodium and potassium channels are voltage gated, which lets local currents provide the threshold potential to open these gates. This is the hyperpolarization, which is the dip on the graph where it's below resting potential, where it's too polar. The refractory period is a short time after an action potential where a neuron can't fire again right away. At first, it can't fire at all because its sodium channels are shut, and then it can only fire if the stimulus is stronger than usual because the cell is returning to its resting state.
The depolarization at the action potential opens the voltage-gated calcium channels, which then the calcium ions are diffused through facilitated diffusion, which the calcium influx signals synaptic vesicles diffuse with the presynaptic membrane.
Is it crazy to say that I have practice Friday from 5 to 6:30? The time changes. The coach just sent out, so it's 5 to 6:30.
The binding of ACH on the neurotransmitter receptors opens the sodium ion channels and allows for diffusion of sodium ions into the postsynaptic cells, and this allows the new action potential is initiated in the postsynaptic cells. And when ACH binds to these neurotransmitter receptors, it is rapidly broken down and it is reabsorbed by the next presynaptic cells, and which creates the cycle again. And this whole cycle is created a cholinergic synapse.
So, when presynaptic neurons are depolarized, they release a neurotransmitter into the synapse. In this case, the neurotransmitter is ACH, or acetylcholine, and this process is exocytosis. This ACH diffuses across the synaptic cleft, which is right here, and then binds onto the receptor protein on the postsynaptic membrane right here.